Today we're here to answer one simple question. Is this safe or not? Welcome to Bugs of C++. I don't have like an intro animation, so let's just get on with it. This video is pretty simple. Could probably have just been a YouTube short, but you know me, we're gonna dive deep. So fundamentally, let's have a look at this. What is actually happening here? We have a getName function which returns a string. It's returning a string literal, so it's creating a new string. This is gonna be using the implicit constructor of string to convert this const char array into an actual string object. We're returning that, here it is, and then we're doing .cstring to get the underlying const char pointer buffer that is held by the string object, and we're sending that into the print line function. Now let me just quickly mention that you of course do not actually have to do this if you're trying to print a string, because the print line function can handle a string object. So if anyone here is new to C++ and you're like, why are you doing that? That's not the point of the video. The problem here, or the potential problem here, is that this string object, which kind of only exists in this context here, is responsible for holding the memory that makes up these characters. So obviously, by that logic, since the string actually holds the const char buffer that makes up the characters of the string, once the string dies, so does the const char buffer. So if we deliberately expand this example to what a lot of people probably think is going on here, if I do const char pointer name equals getName.cstring, and then we try and print the name, this tells a slightly different story. And in fact, Visual Studio is telling me immediately that the pointer is dangling because it points at a temporary instance which was destroyed. What we're doing here is we're calling getName, which returns a brand new std string object, but notice we're not storing it in any sort of variable. It's sort of just transiently, temporarily existing within this line of code. So then when we try and pull out a simple pointer from that object, and remember, a pointer is just an integer, it's just a memory address. So it's not like it's going to transfer ownership of that memory or anything. No, it is literally just a number. We're pulling an int out of this string and storing it within this object. So then getName, which returns our string, that string's not being stored anywhere, means that when we go to the next line of code, that string is gone. That string has been deleted, and it has obviously freed its buffer of memory, which we are still pointing to with our little pointer into this name variable. So then when we go to print that name, the print line function is going to start reading characters from a buffer that doesn't actually exist anymore. It's been freed. But aren't we doing the same thing over here? Is this not the same code? It is the same code, but the difference is where the actual C string pointer is being used. In this case, it's being passed directly into the print line function. Think of it this way. getName is our string, right? Our string dies when we hit this semicolon at the end of our statement. So basically what I'm saying is that this string that we're returning, it is safe within this exact line of code, which includes going into the print line function. Our actual string object is not going to die until this statement, this expression actually finishes. When we drop to the next line of code, it's gone. But within this line of code, it's still alive, which means that this is, in fact, safe. The example below is a little bit different because by our same logic of our string existing within this line of code, yeah, it does exist within this line of code. And what are we doing with it? We're simply pulling out an integer. We're pulling out a const char pointer. So then it clearly gets destroyed after that line of code. And when we go to print it now with name, a pointer within our string that has now been destroyed, boom. Now, if you want to make sure that you and your team catch bugs like this, then you should check out CodeRabbit, the sponsor of this video. CodeRabbit is your AI co-pilot, helping you and your team produce higher quality code. Dev teams are moving faster than ever with all of these AI tools writing your code for you. So how can you possibly keep up and ensure that you're still delivering quality code? Code reviews are super critical, but time consuming. So we need better tools to help us. CodeRabbit is the category-defining platform for AI code reviews, with context-aware reviews that pull in dozens of points of context. CodeRabbit provides you with instant code review comments and shows you the potential impact of every pull request, meaning you can stay on top of every change in your code base. CodeRabbit is a self-improving agent that learns from all of the interactions that you have with it, with customization features that allow you to tailor it to your code base. It helps organizations catch bugs, strengthen security, and ship reliable code at speed, which is why it's trusted by thousands of organizations and open source projects worldwide, such as NVIDIA. CodeRabbit reviews 1 million pull requests per week across 3 million repositories and is used by 100,000 open source projects. Aside from seamlessly integrating into GitHub or GitLab, CodeRabbit is also available in CLI and IDE. So give it a try today and cut code review time and bugs in half instantly. Go to coderabbit.link/Cherno, link will be in the description below. Huge thank you to CodeRabbit for sponsoring this video. I think this is a bit of a common misconception that people have because this looks like it might be dangerous. So how would we then rewrite this so that it is in fact safe? Well, we just need to make sure that the string is stored until we're actually truly done with its memory. So instead of const char name, we would just do std string name equals get name. And then from there, if we really wanted it to be like a char pointer in its own variable, we could do something like name.cstring like this. And then we would provide our function with that. I would just rewrite this like this though. There's no need to pull out the const char pointer into its own variable, but this is in fact safe. Our string that is created by this getName function is going to be stored within this string variable until this string variable name goes out of scope, which in this case is of course going to be the end of our program. So that's it. This is 100% safe. So either of these are technically safe in this specific context. However, this is kind of guaranteed to be safe, but it's really up to what the function is actually doing with this pointer. For example, this is pretty unlikely in practice, I would have to say, but if the printline function decided to take this const char pointer and store it for some reason, and then later in the program, after this line has finished, it would then try and use the memory at that pointer. That of course is going to not be there anymore because the string has been destroyed. Now it would be pretty psychopathic for someone to write a function like this that takes in a pointer and then just stores it without any kind of copying it into its own internal buffer, but just storing the pointer directly. Like that doesn't really happen. At least not with a string pointer like this, but in other cases it can certainly happen. Like if this was a pointer to an object, then by taking in a raw pointer into some sort of function and then potentially storing it, it's kind of like a weak pointer. But again, that would only apply if you have some sort of external object that internally is owning a pointer that will be freed when that external object dies. But the point is, you don't technically know what's happening here. Maybe some logging library decides to buffer the log messages and not just print them immediately, and they would just store the const char pointer. Again, in that scenario, the logging library would almost certainly copy the string into its own internal memory so that you wouldn't be bound by some weird lifetime like this. Another really common example that I see that people are unsure about pretty often is if you have a file system path, so let's do get path, return image.png. If I have a file system path and I need to get a char pointer out of it, how do I do that? And in fact, let's just say that I'm actually storing this properly. So here is my path, and then I want to, I don't know, display it in the UI using ImGUI. Maybe it needs an actual char pointer. So how do I get to a char pointer? Well, file system path does have a cstring function. However, that doesn't actually return a char. It returns a wide string, at least in MSVC's implementation. So that's no good. I need a normal cstring. So I have to do .string.cstring. That is the pattern that most people are used to. And you can see that this can also kind of look crazier if it's like this. So then if I had this and I wanted to log it, would something like this be acceptable? And again, if we apply our rules to it, we have a very transient string here because path.string, this doesn't return a const string reference or anything. You can see it's actually constructing a new string, and then we're calling .cstring to get the pointer to the char array buffer from within that transient string. However, because it's all happening within this one line, and printline will consume and be done with that actual char pointer by the end of its scope, this is in fact safe. I should also note that the reason why specifically this is unclear is because we are constructing and returning a new string that clearly only exists within this line of code. If we had the function getName return a const string reference, so if this was actually stored here, for example, and then we simply returned the reference to this, then this, of course, would always work. Even in that example where I was just pulling out the string like this and then printing it. This is legit now. because getName returns a const reference of a string that is just global. So it's always present and it's never going to get deleted. So therefore this pointer will always be valid, not just within this line. The whole point of this was that it was constructing a new string that only existed within the line of code that it was used in. So you can see that things are a little bit messy here. And that's why I try and avoid, as best as I can, writing code like this really ever. What I normally do is I pull this out like this and I have path.string, and then it's very, very clear here that yes, in fact, I am taking a pointer from this string, but this string is now a proper L value. It's a proper variable. I've made the lifetime super clear. So even though something like this is safe, and the way that this was written before is safe, I still prefer to write it like this. Now, one more thing that I want to say is the annoying thing about this bug is that sometimes, even if you actually do things not properly, so if we go back to this example here, but I change the getName function to use this version instead, this clearly shouldn't work, right? I mean, even Visual Studio says that it shouldn't work. However, it can work. The reason why is because at the end of this line, the memory that this const char pointer is pointing towards has in fact been freed, but it may not have necessarily changed or been rewritten yet. I mean, not much has probably happened between these two lines of code. And so technically, if I run just sort of this section of code, then our result is absolutely nothing is getting printed. If I switch to a release build and I also run this, nothing, again, using MSVC. However, this is where it gets fun. If we have a look at GCC, same exact code, we have this being returned, we're doing .cstring, and then here in fact is our const char pointer string that we're taking out and printing. The result is, well, it says Cherno. If we turn optimization on and we run it again, we get a different result. Name, I don't know. But with optimization off, name is Cherno. What about Clang? Here's Clang. Let's run that. We get a warning, which is nice, but it still prints correctly. Let's try optimization on. Again, same warning, and it didn't actually run, so maybe it crashed. So clearly, this is something that can kind of slip through the cracks, because unless something has overwritten that memory, just because it's free doesn't mean that you're completely banned from using it. So yes, this is something that you need to make sure that you are careful with. And a really good way of avoiding all of this is to just make sure that you basically don't have any sort of transient temporaries, but you clearly define the scope and the lifetime of every object whose data you then use and are dependent on. Hope you all enjoyed this video. If you did, please don't forget to hit the like button. Let me know your thoughts in the comment section below as well. Do you encounter this often? How do you deal with it? Has this ever burned you? Because it's burned me. If you have any other bugs that you'd like me to make a video on, leave them in the comment section below, and I will see you guys next time. Goodbye.